The physics class allows entities and particles to move in a realistic manner. In my engine physics, objects can be subject to linear acceleration, gravity, levity, air drag, and friction. To apply forces, physics objects need mass. Mass is a scalar value that represents the totality of matter that comprises an object. Mass should not be confused with weight, which is the product of mass multiplied by the strength of the gravitational field it resides in. You will weigh less on the Moon than on Earth, but you will have the same mass. The apply force function comes in two versions, one that takes in a magnitude and direction to calculate the force, and another that just takes in the force vector. Air drag is the reactive force that occurs when an object travels through a gaseous medium. Air drag is proportional to the square of the velocity because drag impinges on the two-dimensional surfaces of objects, and the faster an object moves, the stronger the reactant force of the gas molecules that collide with it. I use 0.02 as my drag coefficient. The apply friction function works in almost the same way, except it uses a parametricized coefficient. I use 0.12 as my friction coefficient. You could have a different coefficient for different surface types. Apply gravity increments the acceleration variable by the gravitational acceleration at the surface of Earth, 9.8 meters per second. The normal force is a contact force that acts perpendicularly to the surface of an object. The apply normal force and friction function applies the normal force proportionally to the gravitational force and the dot product of the surface normal and the direction of gravity inversed. This prevents gravity from pushing objects through the ground. The relative velocity is the velocity of the contact surface minus the velocity of the physics entity. I keep all the global physics constants in my Physics Manager class, which uses the singleton design pattern. The update function applies air drag, gravity, and levity if the booleans are set to true for those values. I use Newton's equation to set the acceleration, force divided by mass. To update the velocity, I use the Runge-Kutta integration method. This is a numerical method used to approximate the result of an update step. It provides an iterative procedure to find this approximation by calculating the slopes at discrete points within the update interval. I use the most used form, RK4. It evaluates the result at 4 different slopes. The first slope is at the beginning of the interval. The second is at the midpoint of the interval using the first slope and Euler integration. The third slope is also at the midpoint, but it uses the second slope and Euler integration. The fourth slope is at the end of the update interval. This image shows an example of the 4 sample slopes to approximate the positions along a curve that represents the accurate update interval. The equations to calculate the slopes are as follows. Finally, we reset the force to 0 in preparation of the next frame.